Hi there, welcome to another Maths live stream. Really excited to be getting more and more into depth into discussing actual maths topics. So today we're going to be discussing a whole bunch of topics, and we'll quickly introduce ourselves and get straight into it. So I'll start with myself. I'm Aturana. I'm an online maths tutor. I teach all sort of range from K stage 1 to A level maths, and I'm based in London. So over to you, Nikki, as well. Just a quick introduction.
Hi, I'm Nikki. I'm teaching at secondary, Key Stage 3 to Key Stage 5. I'm based in South Staffordshire.
Nice.
Hi, I'm Laurie. I've taught in a school just outside Manchester for the last 8 years, and I'm just switching to become a subject leader of maths in a different school.
Hello, my name's Andrew Dickens. I'm a local leader in maths education in Oldham, and have been for 25 years now.
And I'm Kirsty. I'm the head of Key Stage 4 at a school in Oldham and one of the local leaders of maths education as well.
Brilliant, thanks. So we're streaming this on Twitter and on Facebook and on our Maths Tutors group as well. And for Twitter, we're using this hashtag Maths Topics Live. So these live streams are interactive. They are led by you as well. So if you're on Twitter, just and something comes up when we're talking, just post us a question, and we'll do our best when we find a right moment in time and answer it and discuss it. So I'll pass it over to you, Laurie, since you've got some.
Yeah, sorry, it might go a bit darker here. I'm just going to close the blind there. So we're going to just kick off by discussing some work that we did in Oldham, just outside Manchester, and myself, Andrew, and Kirsty worked on this during a sort of 2-year project, I suppose, working as local leaders of maths education. And it was one of the things that came up during that big project was one of the classic huge topics at secondary school level, trigonometry. And so we sat down and started to think about how can we sort of pull it apart and put it back together in the best possible way. We're going to try and sort of give a quick summary, really, of where we got to with this today. And in a nutshell, it came down to we decided that we would settle on the unit circle as being the approach that we would take. There's sometimes a bit of I suppose, I don't know, there's so many mathematical debates, but there's sometimes a bit of an argument as to whether to use the unit circle or to whether to go for another approach. But the more we sat down and thought about it, the more we saw lots and lots of benefits. So the big thing that came out of the work was that I think there's not necessarily one way in which you can do it. It's such a huge branch of mathematics, and I take sort of the point that people like Mark McCourt and others that have been on some of these feeds with you previously, Atul, some of them have said, if enough research and enough history, enough experts have put their minds together, there should be at least some specific ways of going about the structure of the mathematics that will be better than others. And I completely and utterly take that. And I'd like to think that we thought about it enough to produce a really strong approach. But that doesn't mean to say it's different, that it's the same as the way other people have done it. And yeah, I'll show you why in a moment, because in lesson 1 we do something that sometimes people would do it in the final lesson of GCSE almost. So it kind of flips it on its head slightly. And to show people what we used, I'll just flip my camera onto a visualizer, because we actually used this, I suppose you could kind of call it a manipulative, a physical model that we've got here. So this is an A3, as you can kind of see, laminated piece of paper. And this was the kind of one of the game changers with the work that we came up with, or we feel it was anyway, because we realized it was such a dynamic topic, and it was all about sort of things changing and seeing what happens. And it's it's called circular trigonometry a lot of the time, but not so often in maths classrooms. So we eventually designed this model, and this is just one of the early prototypes. So you'll have to excuse the post-it notes covering up what we hoped would be a charity. We had a grand plan to sell them for a small amount and give the profits to an educational charity, but we need to stump up a heck of a lot more money for that to work. So for those who can't see, well, let me just zoom in a bit, and hopefully if you can make that out, what we've got here is a set of angles, 0 on the positive x-axis. We've got it going up in 15 degrees if it's a bit small, 15, 30, 45, 60, and so on, anti-clockwise. And the crucial bit to give this the dynamic element is that we've got another bit of acetate over the top that allows it to spin around. Okay. And so the advantage of this is that in lesson 1, the students can have the models and they can use it, in the pairs. And what we can do is start to have a play around with things, with students in year 7 and say things like, okay, well, first of all, what do we know that, if we put a dot on the circumference, a mark, what do we know that goes around and around? And we can liken it to the sun. And we've got a whole sort of structure that I won't go into now of possible questions that can get the students really thinking about the model and why might it go anti-clockwise and not clockwise. And I might not give away all of our sort of little responses here, but feel free if anyone is watching and wants to find out more, then do ask. But what we eventually lead to in this first lesson is a mixture of, the way I see it, and Andrew and Kirsty, you can tell me if you agree or not here, I see it as a bit of a mixture of these worlds that we see in education, maths education at the moment. We see a kind of, Rosenstein's principles and direct teaching, and we also see this sort of problem solving, investigative, and I see this as like a nice marriage between the two, because we direct some parts of it, because we were really lucky to go to other schools and try this out with all sorts of different classes. So it's had a real good test run, and we found lots of different issues. So it's a great one to visualize on the board or on a visualizer for the class. But if the instructions aren't very explicit, we found that students would mark things in the wrong place, which is this, because what we actually tell them to do in the end, after a bit of play, is to put a mark at the 15-degree angle. So if you mark it at 15 degrees, and we ask them to measure this perpendicular height, so the height perpendicular to the x-axis, and it's all got a bit of a kind of, it all kind of comes from the students, but eventually they sort of suggest that a table is a good way of recording this. So you'll end up with something along the lines of angle, and you might have something like height perhaps, and we might sort of discuss the importance of having some units in there. And we're even sort of subtly picky, I suppose, and I've not got a sort of traditional ruler here because this is my little gadget and gizmo for drawing circles, but we're picky in the sense that we suggest that they should start with the 0 this way, or at least when we model it, with the scale on the ruler going upwards, because it's very, very easy just to measure it the other way around. But of course the y-axis starts at 0 here and goes positively up that way, so it's just a subtle thing that helps to ensure a little bit more consistency. And so you're getting to measure, for 0 degrees, for 15 degrees, for 30 degrees, and so on, and they'll put the corresponding heights. And the more we sort of put this, what ended up being a kind of 5-year scheme of work, the more we put it together, the more we sort of realized how, well, to use one of the sort of current buzzwords, I suppose, interconnectedness, or that wasn't the word I was after, actually. What's the word I'm after, folks? All the topics put together, mixed into one problem. I'm sure someone will be thinking of it. Oh, you're on mute there, Andrew, but it's not interconnectedness, although I love that one. Anyone got it? What's the word I'm after?
Holistic.
It wasn't what I was after, but it was something like that. Yeah. Such a buzzword, I can't even remember it. That goes to show.
Yeah,
me.
interleaved.
Interleaving, thank you. Yeah, interleaving is what I was after. Yeah, a heuristic approach, interconnectedness, like I say, and it's all that kind of thing, because we notice things like, well, small things, I suppose, 15 times table and multiples of 15, but we've got things like obviously measuring, as we've mentioned. When you've got the height, you get students starting to spot in their minds what is a pattern, and quite often we'd get them to, they'd see the first 3 entries written in, and it was amazing how many would then make an assumption about the following entry, and that's almost as if they were tuned into this well, I suppose in arithmetic, additive reasoning, which we know students are quite attuned to. So they want it to go up in this by the same amount, like an arithmetic sequence all the time. And for those who know what this is about, you'll realize that's not going to happen. So that was an interesting point about assumptions. You then get all sorts of discussions coming out about measurements, errors, inaccuracies, because of course one pair's measurement isn't going to be absolutely the same as another pair's measurement necessarily. And anyway, they work their way around measuring every 15 degrees. And of course, they get to 90 degrees. And I'm sure it's not beyond sort of the maths teachers watching. Depends how much experience we've had with it, I suppose. But when you measure 105 degrees, if I mark that on, so 105 degrees is going to be this height. Oops. And hopefully it's not too hard to see, for us at least, that that's going to be the same as if we'd measured 75 degrees, which would have been this height dotted. And there's all sorts of symmetry coming into play here. And as the scheme develops, we've got a lot of stuff on transformations and things as well, but using the consistent model of this unit circle, laminated A3, manipulative, I suppose, if we want to call it that. And what's really nice is that in lesson 1, we've got students that realize the pattern straight away and then immediately go on to fill out 105 degrees, 120 degrees, 135, and then the entire rest of it, including some good questions about what happens when it goes beneath the x-axis. Okay, and so other students, as you might imagine, plod along perfectly acceptably and keep continuing to measure each 15-degree section, which incidentally is called a card-garger, if I remember correctly, when it was originally used. And actually there's a very good reason as to why we've broken it up into 15-degree increments, apart from the fact that it gives a reasonable number without being too much, we feel. But yeah, so you can start to use the class to kind of keep them together, but to sort of make use of the students who have spotted the pattern, to help out those who haven't. And I mean, that comes down to the skill of the teacher, I suppose, to kind of facilitate that in the right way. Depending on the class, we've then found, I'll just flick it back onto my video for now. Yeah, we've actually found that with some classes, we've then got on to the next stage. With other classes, it's been the next lesson. But we've then, talking about the interconnectedness and interleaving, we've then sort of done a bit of work on plotting and graphing as well within this topic, and found that actually we've got mixed abilities, bottom sets and top sets, who are then graphing the 15-degree increments of their angles. They're plotting it against the heights that they've measured. And I mean, I'm sorry, I get a bit lost as to whether I'm talking to students here or teachers, but obviously from a teacher perspective, we all know it's the sine curve, don't we? And it's just brilliant. You've not mentioned anything, and I'm not sort of going to sit here and claim this is a magic formula for how it works or anything, but there's just so many patterns, and they get to play around with that early on before they get to maybe GCSE level and hear about this mystical formula, or what would I call it? Not a formula, function, sorry. But I think the main thing as well that it gets across is it gets the inquisitive questions from the students, or at least that's what we've found as we've developed it and as we've practiced our own questioning, having repeated it a few times, because we've suddenly got students asking, what happens if you go in between 15 and 30 degrees? What happens if you go past 360 degrees? Can you go past 360 degrees? Can you have an angle bigger than that? And sometimes that comes from the students, and sometimes, if the time's right, we can pose the question. And you get onto all sorts of things then, like a negative angle, and what would that mean? What would a 375 degree angle produce, and so on. And because you've got that physical model that is circular and moves around, it's very easy to sort of show that in a different representation. And I think it does really help to get that idea of the infinite nature of it in either direction, because you can just keep spinning the circle. And you can have students that typically haven't done brilliantly on attainment wise that are suddenly screaming at the answer. You just sat down next to them just in the middle of the investigation, and they're telling you immediately what sine of, 3,600 is. They just shout out 0 straight away because it's so obvious for them. And you can get things like, we were very careful when we were putting this together to make sure we didn't criticize students, because at this point they've got points plotted, of course, and it's not necessarily obvious that they should join them with a smooth curve. So we were very careful not to, we've planned this, so it would be probably year 7. But if they've joined them with straight lines or curved or whatever, we kind of play that a bit carefully at early doors. I don't know if anyone wants to comment on that so far, but otherwise I'll kind of show you where it leads to, but in a bit less detail.
Yeah, I will, if that's all right, because this really intrigues me, because obviously you've said unit circle as the introduction to trigonometry, and it's not something, as you said, I've ever done before. We've always looked at the ratio between the sides rather than the unit circle. So it's really lovely and interesting to hear a different way of introducing it. My first questions are, first of all, do you mention triangles when you introduce this, or is it just for circles to begin with?
Again, Andrew, Kirsty, do feel free to chip in, but my experience is that it falls out quite naturally. So I did that all very rushed there, because there's just, I can't really condense 5 years of theme, obviously, but if I do put this back on, if they were looking at the 30-degree angle, one of the things that comes out, so if we look at 30 degree, for example, is I almost did it when I was trying to illustrate it earlier. I didn't really know where to put it. It makes sense to extend this and put the radius in to make sure you are accurately measuring the 30 degrees, because we've deliberately left it a bit short. And because this is the length that we are looking at measuring, and there's a bit of a discussion as well as to why on earth would we want to measure that, which I think is a very fair question. Sort of why historically might what we want to work out the physical height of something from a distance. But the triangle comes out very naturally, usually, well, only because we've done it, sort of over the couple of years or so, at some stage in the early sort of section of the year 7 scheme, it seems to come out usually, like I say, at the start here, because it's just more natural to draw it in to make sure you're accurate. So we're definitely talking about circular stuff a lot and the circular motion, but the triangles are within that. So you can I suppose you could start to ask, where else would you see this triangle? If you're going to ask it on a sort of more basic level, and you might get students drawing them in the 4 different quadrants, and you'd get that 30, 60.
It's a good prompt. I like the prompt for the discussion point, that say from the height you suddenly, and the angle, you are suddenly getting a right angle triangle without actually saying we're looking at right angle triangles.
Yeah.
And then
actually, sorry, Nikki, there is a sort of an example of a lesson questioning script that we've used when we've delivered the lesson in schools in Oldham. And it does talk about the focus of the lesson being on circles and the symmetry of circles. But those right angle triangles definitely pop out when they start measuring.
Absolutely. It's, as I say, you get that connection really early on, because obviously when you're doing it, introducing trigonometry and looking at the ratio of sides of the triangles, you don't mention circles. And as you said before in your introduction, it's quite common to leave the circle side and the unit circle towards the end. And even maybe for some of the like higher foundation students, you might not even mention circles and the relationship at all. But this falls out naturally that there's a relationship between the triangles and the circles straight away.
Yeah, it is just that. I think it's that periodicity, isn't it? The sort of never-endingness of it becomes almost so trivial. It's really obvious kind of thing.
Yeah.
And I say that with a bit of trepidation, but it's really not obvious the way we normally do it, because the way I would normally have done it in the past, which is focusing only on triangles, because that's naturally it's the principal triangle. It's that triangle that's in the first quadrant when you focus only on triangles. And so that kind of comes into play a bit later when we sort of start to remove the circle slightly and you're looking just at triangles. That kind of comes to a sort of the idea of or reorienting things so that it lands in that first quadrant. I've just noticed some of the you just reminded us, Andrew, when you said some of the questions. I've just got up some of the prompts that we did jot down. What do we notice about pairs of angles that have the same height? Because that's interesting. You're going to get things like 30 degrees and 150, 45 and 135. They're going to give the same height. So you've kind of got this corresponding angles having the same sum of 180. You've got what happens if we consider negative angles? Can you have a negative 30 degrees, and what does that mean in this context? And also we talked about going past say 180 degrees or 360. So you could have, I mean, you could consider, for example, 210 degrees and negative 30 if you've broached that sort of area. And of course, you've got a little bit of your interleaving going on there, because you're back to addition of positive and negative values there, because 210 and negative 30 sum to 180, which you've just discovered always produces the same height, which we know is going to be the sine value is to come. What about angles which have a difference of 180 degrees? Can we ever get a height greater than 10 centimeters? One of the things I didn't mention earlier was that the circle's been deliberately measured so that the physical one that I'm holding is 10 centimeters in diameter.
That was one of my questions.
Which is a really nice, we can see it against the size of, relative to me, it's a nice size to work with. It's big enough for, like I say, if you want it to work in pairs, not that it has to. But also, of course, we work in a base 10 system. So all of the values that come out that these students are working with year in, year out, because we keep using this model. So right from that first lesson, when they're measuring the height for 15 degrees, 30 degrees, 45, and don't forget, these are going to be the key values, these cadages. The digits in them are going to be, 10 times more than they would be if it was the sine value of those angles, because that would be with a unit circle, radius 1, not radius 10. But we work in a base 10, so it's recognizable. So we've got things like look at the height for 30 degrees and look at the height for 60 degrees. 45 degrees is in the middle of these, so you can have a little bit of estimation, a bit of prediction and guess and check kind of thing. What would the height be for 45 degrees? And the temptation, of course, is to hit in the middle and to interpolate perfectly bang center, but it doesn't work like that. That's not actually what's going to happen, and you can start to get that idea across. You can even. I mean, it's really endless how far you want to push it, because you could even look at sort of what is effectively A-level-ish ideas and ask about the height of 30 plus the height of the 60-degree angle. And does that or does that not produce the same height if you sum the 30 and the 60 to get 90? So does the height for 30 plus the height for 60 equal the height for 90, essentially? And you've got these kind of ideas going there.
It's very, very neat. It's something just. This is really good. Just to go. I wouldn't have thought of it to introduce with the unit circle. I would do that more later on, or nearly at the end. But it makes perfect sense that the way you've described it, because there's so much going on there. There's just the very fact that there's angular displacement. The fact that there's a difference in angular displacement can go in both directions. You can have a displacement beyond 180 degrees, and the fact that they plot them as well, and then they already got this kind of sine type. Even if they join them up with straight lines, you've got the idea of periodicity.
I like the displacement, the use of the word displacement there, because that, of course, might come in through science typically, but that gives the idea of a distance with a direction attached to it, doesn't it?
Yeah, I've just got my physics hat on, where you have angular momentum and angular displacement, etc. Well, you can of course you can use that in maths as well. You can use the idea that it is an angular displacement. It's really, really neat.
I can show sort of briefly where it leads to, but sorry, Nikki.
And I was just going to say, did you say you did this as a year 7 lesson? You didn't introduce it in year 7, or was it just that you had some year 7s and you did it with them?
In the early stages, probably a bit of both. Would you say, Andrew, Kirsty?
Year 8 in the early stages, but the idea was to use this representation and to use it consistently throughout the 5-year journey. And that sort of comes from the mastery program, because we're all, as local leaders in maths education, we're all part of the teaching the mastery specialist program, secondary, with NCTM. So the idea of balancing conceptual understanding with procedural fluency and a consistent use of a representation to gain a deeper understanding of the topic. But Atul mentioned physics. At the start we asked children what the most symmetrical shape was, and you can even go Brian Cox. There's a symmetrical shape seen throughout the universe in all scales, and they come up with planets and suns and moons. And then Laurie's talked about, thrown in a question like, there's only 180 lines of symmetry in a circle, isn't there? And children discuss that, and the idea of infinity comes up, and that sort of links nicely to the wave. Does the wave go on forever? And where do we see circles in everyday life, and where do we see waves in everyday life? So there is a nice kind of link to science throughout it, obviously.
That's just reminded me, one of the biggest misconceptions when we ask we thought it was a cracker of a question, because it's so easy to throw out there to a class, what's the most symmetrical shape that you just mentioned? And we got some really common wrong answers, didn't we? Well, I say wrong, all the students had good reasons for choosing them, but anyone have a guess which shapes came up as the most common that I would personally would say were misconceptions? Symmetric shapes.
My immediate thought is regular shape, so either like square, hexagon, octagon, those sorts of shapes.
Equilateral triangle, maybe.
Yeah, no, it was square, and hexagon was very popular. I think hexagon was the most commonly cited one, and then square, if not circle. Yeah,
interesting.
I'd imagine that's possibly because when they do like symmetry to begin with, it's the one where they've drawn the most lines of symmetry on.
Yeah,
because I don't suppose imagine at Key Stage 2 they wouldn't put circles in just because they'd be drawing lines forever. So it's not really like a SAT sort of question to ask with a circle in there, which is a shame because it takes away that conception of what symmetry is.
And Laurie, do you remember talking about once you got onto the circle probably being the most symmetrical shape, and then talking about angles in circles and degrees and the number 360 coming up?
Oh yeah, it's a bit of a
thinking that. So Laurie had a great sort of history of maths kind of questions and answers that could go on, that sort of that engages the students because they can see that it's real world stuff.
We got our first Twitter question based on this already. So Mr. Taylor Matz, love how the unit circle links into the trigonometric ratios. Any link with exact trig values? I'm assuming that means when you're first teaching it at year 7, year 8, when in the context you're doing it.
Yeah, we do obviously look at that at some point. It came a fair bit later on, partly because they need to have kind of a lot of fluency and understanding of surds and being able to manipulate surds. But also because an awful lot of it came. What we really tried to do is match the history, in terms of the way that it actually progressed and developed throughout millennia over time. And the real reason for that was not just for the sake of it, just because it sounds nice and it's nice to follow and match the history, because that's what we fancy doing. It was more because it's going to sound a little bit grand now, but almost kind of a theory of evolution kind of thing. Like things have adapted over time, because you start to find the best ways, and they often do go in a natural sequence. And when we actually sort of researched a lot of the history, we found things like the tangent function. That was a lot later that was discovered, and that was in use than sine and cosine. And then when you sort of dig a bit further, I'm sure that there are probably people watching know that cosine was originally before cosine, it was usually written as co-dot-sine. And that really, before that, was just a shortened version of complementi sinus. In other words, the complement of the sine. So it's, if you've done the work early on that we were looking at there with complementary angles, those angles that sum to 180, like 30 degrees and 150 degrees, the students are really, really familiar with the idea that complement angles will have the same sine value as the years progress. And so it becomes very, very natural to do sine and cosine together, because they're like brother and sister. They're almost the same thing. You can't really have one without the other. It doesn't really make sense otherwise. So the tangent's a bit of a different kettle of fish altogether, really. And of course it's amazing it's got those links, and there's a beautiful way that we can kind of show that sine over cosine produces the tangent, which is just a lovely result. But that's not necessarily obvious early doors. And we've only included things like that, which is technically AS level in England, because it makes use of so much similarity in things. It's almost worth doing for the interleaving practice, and not so much necessarily for the fact that you get this nice result of sine over cos is tan. Any more questions on that at all? Or
just a follow-up from Mr. Taylor Matts again. Could you then use the unit circles to go to area of our triangle being half AB sine C?
Yeah. I mean, there's a danger we could talk for 3-4 hours on this. Essentially, when we mapped it out, we tried, didn't we, Andrew and Kirsty? We tried to have this as the consistent model that would slowly, over the years, maybe you'd use it less and less. But it could all just be done on here. And we know that kids love working on whiteboards, and students are really responsive. They'll have a go kind of thing. You don't just have to put one student on the spot and ask them and then judge the whole class's understanding on their response. They can all have a go, and you can wander around, they can work together. And so a lot of the work actually just comes from using this. And you'll notice that we didn't, although it is 10 centimeters, there were a lot of small decisions that had to be made, such as we didn't actually write any scale on the Y and X axis at all. So we are then free at any point in time to start putting our own scales on it, and we can determine the length of the radius if we want to, which comes under another discussion about scale diagrams and drawings and so on. And then you can start having students working on this, and you can go to a coordinate system as well, because you've got the X and Y on, so you can do it with coordinates. And the idea was that we actually just keep using the model for lots and lots of things. So certainly area of a triangle, but also midpoint of lines, or like I say, coordinate work, that kind of thing. Yeah, definitely. That's what we planned it as.
You could even go into Pythagoras and the equation of a circle.
Yeah, because yeah, it works perfectly, doesn't it? Because as we were putting this together, we thought there are more and more. I know I'm sounding like a real advocate of this. That's just the way it's panned out, I suppose. More and more things that come back to this as a basis from which other maths can develop. So yeah, like Andrew says, if you put a mark on, I lost my pen, but if you put a mark on and you've got this right angle triangle, again, a lot of people watching have probably seen this, but in case they haven't, of course, if they've done Pythagoras and you've got something like the value of a, b, and c, then of course they'll be aware that a squared plus b squared gives c squared, and of course that is essentially the same as x squared plus y squared. If this is the x distance of the point I just drew up here, and this is the y distance of this point, you've got x squared plus y squared equals r squared, which is of course something that needs to know at GCSE. It's the equation of a circle centered on the origin. And I mentioned transformations earlier. If you know, for a high flying bunch of students, you might then talk about transformations and how that might affect things, you know, and look at translations there and get the, I suppose, A level version of the more generalized x minus a all squared and y minus b all squared. Yeah.
In the 5-year plan, Laurie, the exact trig values and proving the trig formula, it comes up at the end of year 10 and then year 11, doesn't it, I think?
Yeah, I think so. Yeah. I think I was just mentioning that before, wasn't I? That was, like I say, it came about a bit later in the sort of the development, really, of the trigonometry over time. And when you sort of read into it, it becomes fascinating as you realise this was an incredible challenge. Really, it was a real sort of battle over time for how can we find out the sine value of a given angle, because they wouldn't have a calculator sort of to rely on. So it would be a case of, well, we need to use what we've got here. So sine of 30 degrees might be one of the first ones that we look at, because actually it's got some brilliant properties that make it not too bad to determine what sine of 30 actually is. Okay, and you can use bits of knowledge like Pythagoras and other things to work that out. But you try doing sine of 40 degrees and all hell breaks loose. So we start to sort of follow, I might have a slide, not a slider. Sorry, the thing I keep referring to is the actual sort of document that we typed up. If I flick back to the camera, I might be able to show us. Moment. I'm not expecting people to be able to read this. But here are the cadages: 0, 15, 30, 45, 60, 75, and 90. But this is the actual order. If you can just about make this out, this is the order that they were originally sort of discovered, I suppose, in. It was 90 first. This is just for the ones between 0 and 90. 0, I suppose, being trivial. 30 came next, then 60, then 45. Okay, and up to this point, they're not too bad. And experienced teachers will know instantly the kind of associations that the 60 degree has with, you draw that equilateral triangle, perhaps at GCSE, or the 45 degree one, perhaps where you draw the isosceles right angle triangle, so you get the 45 degree angle. All of that comes out, you see, but we just happen to do it on the circle model. The 15 and 75 come in through compound angle formulae. You start to make use of ones that you've already discovered, and that becomes quite a common approach to get other ones. If you get some, then it might unlock others, but some of them are just painfully hard. These ones aren't too bad, and if anyone's wondering why on earth what this is, if you can make it out in this next column, I can't remember what it is now. Is that 600 million? That's because of this fella, Regiomontanus, who used a radius of 600 million, if I remember correctly. And that was because they refused to use non-integers. They used to love working in integers only, and bad luck and deemed really foul play if you try to break an integer. And fraction means to break, doesn't it? Not from Latin, I think. I'm going to get this wrong. Fractare or something. Anyway, And so he scaled up his radius to such an enormous amount that he could actually get very, very accurate values. And I'm probably spouting an incorrect fact here, but at the time of when I wrote it, I remember checking it. I feel like it was way more accurate than the calculator spat out, which I just thought was absolutely nuts. This guy got no calculator. He found sine of, I don't know, 75 degrees better than our calcs can do it.
It's amazing.
Yeah, it's really nice because you just suddenly have this wow moment of, oh yeah, like someone has to tell the calculators how a way of figuring it out, and we had to figure it out somehow initially. And yeah, it's really clever, really clever.
Well, we've got, I think this leads on to it nicely actually. Anthony Daniel Joseph's asking, is there a blog post with all these ideas and some teaching resources on? I'll watch this back, but I do love these ideas.
That's a good question. Andrew, Kirsty, again, you might want to chip in. I think my instant reaction is we've got this enormous document, but to do it a bit of justice, and this isn't to kind of keep it to ourselves and hold it, you know, we wanted to do it justice in terms of giving it a real test run before we just kind of, you know, say, look, this is great, and then it's just another sort of thing that gets washed up. So it's actually going to go on. Do you want to talk, Andy, about it's going to go on like a year trial, I suppose, isn't it, in a work group?
Yeah, it's going to be the focus of work for next year's Northwest One Maths Hub problem solving work group. The work group's the problem solving work group's been running for, it must be like 5 or 6 years now, and it's grown from sort of less than 10 people to way beyond 40 members. So if anybody wanted to, you know, join that group, it's open to secondary school maths teachers in the Northwest. So Northwest One Maths Hub problem solving work group, and you can access invitations to it or details about it on the Maths Hub website. So there's a Northwest One Maths Hub website, and if you go onto there and follow secondary professional development, there will be an invite to secondary school maths teachers there to join that group. And the plan is that the document that Laurie's talking about, it's like a 5-year plan, if you like, using the unit circle model. That will be trialled in schools that attend that problem solving work group next year. And it's an open invite, so it's anybody interested. So I think, is that right, Laurie? In the first instance, that would be the way to sort of get involved in using it.
Yeah, well, that'll be a direct sort of being able to collaborate with other people who are trying bits of it as well. So you'd get probably a bit more out of it, would be my my thoughts. So yeah, it's absolutely not me trying to withhold anything at all, because we put it together to sort of share, really. But yeah, we thought it'd be nice to have a real kind of action research, isn't it? Essentially, you know, it's teachers grouping together, and it's not just one school. It's, you know, sort of nominees, I suppose, from different schools all coming together. So it's a nice way of trying stuff out and reporting back. That's the idea, at least, anyway.
Yeah.
So now you've introduced it to us, is it something that as you trial it out, you'd be able to sort of like report back on, like, as you go along, rather than leaving it to the end of the year, to get the interest of us, like, who aren't part of the Northwest, to see what's going on, and so say after the year, then we can get further information once you've done it.
I can make an effort to try and do that. Yeah, with taking a new sort of lead department role, I'll do my best. But where I've got time, I'll try and sort of. It says draft copy anyway, so it's all about making the improvements as it goes and finding out the issues. But if I can, it'd just be really, it'd be really interesting now you've introduced to see those schools which are piloting it, and like from your problem solving work group, as they go along, what sort of things they're finding out. Obviously not sort of like all the time, but just as little snippets of it, just to see how other schools are doing using it to begin with.
I mean, Nikki, I can ask the Maths Hub administration whether it would be okay because all the PD and the meetings next year will be done remotely, at least until March 21 at the earliest, or at the latest. So you may well be able to attend those meetings by Zoom, and then you'll be able to keep in touch with what's going on.
Yeah, that might be a good way.
I have to ask the hub lead whether that would be okay.
I mean, as
Yeah,
pointers.
You've really piqued interest here, and I'm assuming there's going to be others as well listening, watching, that you'll pique their interest with it. I mean, now you've done the introduction, could you give like a little overview of where it leads to, onto the like which direction you'd go into in the next sort of like few lessons? And
yeah, this is probably the key part in many ways. I mean, there's a heck of a lot to it, but if I flick back again, my
I imagine
pink laminate. So this, for me at least, and again, I keep going back to Andrew and Kirsty said this might be the same for them, but for me, this was arguably the hardest bit to undo in some ways. So if I draw, so let me get that on the screen. If I draw a right angled triangle, forgive me for drawing it in such a typical manner as I have done, and terribly inaccurate, not to scale.
Looks good.
There is a reason why I have drawn, you'd normally not catch me draw one in such a standard form like as this, and you rotate it around and whatnot, but there is a reason, and that's because of the model. So if let's just say, for example, and we've been working in centimeters, let's say, so if we gave this setup to a student who's been following this sort of approach to the early doors of trigonometry, and you asked, what is the length of this value here? Well, what have they got to go off now? For us, it's labeling the sides. I say for us, when I say that, I generally mean me and my previous experiences in school and as a teacher. Okay, so forgive me there. But I know for a lot of teachers, it's label it as O, H, and A in whichever order. Maybe that's just the order I tend to do it in. That's why I said it in that order. And then I'd go to see which of the SOHCAHTOA ratios it is. And I know there are variations on this, but essentially I need to figure out that it's going to be the sine ratio, and something to do with opposite over hypotenuse, and how I rejig the formula will be dependent on how the teachers taught me. But try and remove yourself from that for a moment, and remove any knowledge or any understanding that we have, or predispositions about trigonometry in the way we were taught, and just think, well, what do these students know at the minute? And you could almost ask them this and kind of lead them into this a little bit for the time being. And what they know is not what this length is, but they do damn well know, or at least can figure out. Hopefully we've broached the topic of drawing diagrams to scale, so we can talk about things not being to scale here. But were that 10 centimeters, is that not just what we were measuring earlier on the model? Because we can put on our 30-degree angle, and we can measure off. We know that the radius is 10 centimeters if we were to measure, and this is accurate as 10 centimeters. And this is 30 degrees, that's what I've just set it to. But I don't need to faff too much with protractors. I mean, I can do some work on that at some stage, but it's labeled on there for me. So all I need to do is measure this. And if needs be, I can just go back to my my lovely tables from lesson 1 last year, because the teacher collected everything in a folder to create this big picture. And I don't even need to measure it again. I can actually I know what the height for 30 degrees is. And depending on where we're up to in the scheme, we might know the word sine at this point, we might not. It doesn't matter too much, but we'll know what it is. And so the kind of point, if you can see where this is going, that this is leading to, I probably should have stuck with my own drawings, is 10 to 80, scale factor of multiplying by 8. And because this is measurable from the model, we can just scale it up by timesing it by 8. And you've just found that missing length. And it was just multiplicative reasoning. It was just scaling something up, which I say this very hesitantly, but can be at times quite natural to students. It can not be as well. But our experience was that the students found that quite a natural approach. The fact that one thing, especially because we made it 10 centimeters yet again, another reason for why we chose that, it was quite easy to see that 10 to 80 was times by 8. And in that instance, we found hardly any, if any, cases of that additive thinking. Nobody thought add 70 centimeters, and we prepared for that, and we thought that might happen when we planned it, but it didn't. And maybe that's just because the 10 times table is so well known and so well versed. So it became really, really straightforward for the students to suddenly they were doing trigonometry, and we'd hardly, they'd already done graphs. Now I know it's only a touch of the surface of things, but then they found in sines, cosines exactly the opposite, not the opposite, exactly the same idea, but you'd be trying to figure out the complement of the sine, okay, which there's a lot of work that goes into that as well, but it's the same idea. Just measure it off your model and then just scale it. And then it doesn't have to be 80 centimeters. So we produced a worksheet where it's 15 centimeters. Maybe that's more tempting to add 5 instead of times by 1.5. Suddenly forcing them to make it a bit hard. What if you make it less than 10? What if you reduce it down to 2? And then what happens if you go to really awkward numbers? What if you make that, I don't know, that hypotenuse 7 centimeters, or, whatever you want, really. You can see where that's going. And then again, it's all that multiplicative reasoning coming in. So I'd say that's the key mindset change for me, really, and for us as teachers, way more than the students. That's just what they know. That's their experience from scratch. They don't know anything else apart from this model. So I think that the hardest thing has been us to kind of think, no, stop the way we know. Let's just bear in mind that's all they know at the moment. So that's a sort of flavour of where it goes to, I suppose. And to reference one of the things from earlier about when I drew it in this principal position, is that you can't draw a right angled triangle with like 150 degree angle in it, for example. So you might need to reorient it and use all those patterns that we've worked on early on about complements. So 150 degrees being the same, or giving the same sine value as 30 degrees. And if that's really well known, then they can just use that to create a principal triangle, knowing in the full knowledge that it will give the exact same as a triangle, a congruent triangle in this section over here, kind of thing. Anyway, I'm babbling on a little bit there, but that's the idea.
No, it's really good. I mean, we've already had Mr. Taylor Maths double check. It's at nw1mathshub.co.uk. Event mastery. Maybe Andrew Dickens, you can confirm that, but there might be a whole rush towards your joining your Zoom calls on this one, because it's already out there.
Okay, I can check with the hub link tomorrow.
Yeah, it's on Twitter anyway. So
well, in the first instance, if you use the website, no.
Yeah.
At what point do you go to the actual unit of 1? So sort of like linking with your calculator value? Because I mean, obviously, the conceptualization of what you've done there is, I love it. It's really good. But then at some point, they're going to go to the calculator values and go, oh, and obviously they should be able to connect straight away the 10 centimeters and the 1 centimeter, because you've used such a sensible radius.
We want to keep it. I mean, there's no rule, is there? This is just what we've put together.
I know, but you've looked into it, and sort of like you've got the ideas. It's nice to know. Yeah,
I think we did it in year 9, just so, I don't know, 3rd year. I mean, mainly to allow, you still got to do the rest of the curriculum, and we hope that we still, we've already talked about Pythagoras and area of circles and midpoints, and lots of stuff's coming up within it. So we're hoping that kind of collects a lot of it and does it in a mixed way. But I think we put it in the 3rd year, if memory serves me correctly. And I'll just quickly show you the idea. So again, it's going to be a bit small, so let me just zoom in slightly. So we've got a table here, which it's not an unfamiliar table for a lot of people, of these cadages, like I say. Oh, it's got some other ones actually. It's going up in 5s, and we essentially say at some point that wouldn't this help that we've got this table already, and they've kind of already drawn it up, so it's great. But we said that when we show them the calculator button here, we say we need to settle on a convention. It's great if we've got a table that is easily accessible. Brill, we don't need to bother with the measuring it every time, which is a little bit cumbersome. Let's be honest. I'm 3 years into the the scheme. They're like, yeah, it is. I was quite happy to do it, but actually, So we say, great, well, actually, a lot of the hard work has been done for us and it's being stored somewhere. And for a while, we get them practicing with the table. I was going to say physical table, but, you know, actually seeing the values there. And it's then only then, I mean, that's with a hypotenuse of 1. And it's only sort of after a bit of work with that it goes to the calculator and can you check and confirm and so on. But yeah.
No, that's great. I really like sort of like thinking about the process and how you've gone like from one stage to another stage to another stage, and what you've decided to introduce first and what you've decided to keep back until that understanding of say the height. They've got an understanding of height before you then go into an understanding of the length before the connections. Do you try with different size circles as well to see that the proportions with the height are the same? So like when you did 10 centimetres to 80 centimetres, would have measured with a 5 centimetre circle and realised, well, at 30 degrees, the height is half the radius?
Yeah, I'll just quickly add on again. It may be a familiar image. It's a bit rough, sorry. That kind of idea, yeah. We've just put in another vertical line.
Yeah.
And we could
you don't even need to put the extra circle in, do you?
We could do. I'm just not going to be able to draw it very well.
Well, yeah, no, but
yeah, and arguably that covers up a little bit of, it hides ever so slightly the similar triangles. You know, if we're to draw these 3 triangles that I've got there out, you know, that are quite a lot of the work that goes on in the build up to the things that follow is all about similarity and really doing it in. I'll hold my hands up. I think I've not done it in anywhere near the depth that it deserves earlier in my teaching career, and I think the only way of understanding a lot of this is having a strong knowledge of similarity. And in that early instance with the, you know, where we had the 10 and the 80 centimeters, we relied on it being a little bit intuitive. And even if students didn't get it with a bit of guidance, they'll be okay. They can figure out they can see what's going on. We really tighten up and formalize that and actually really focus heavily on similarity, sort of further on down the line. I don't think you can do what follows otherwise, really.
Yeah. Well, just from your brief overview today, you can see how many of the different concepts are being pulled out through this model, rather than through just the relationship between the two sides on a triangle model that, I say, is most commonplace in what we've been teaching trigonometry as.
I think that's part of the mastery program, to sort of move away from that belief that teaching tricks and procedures, you know, eventually leads to understanding, and you know, aiming for that deeper understanding. You know, moving to the belief that teaching structures and representations, that leads to the understanding and therefore fluency with procedures. So it's a different. But I was interested in what Laurie said earlier about, you know, there doesn't necessarily need to be a conflict between inquiry or problem solving, inquiry based or problem solving approaches to learning mathematics as against direct instruction and the Rosenshines principles. And I think, you know, Laurie identified that within these lessons there is sort of a mixture of both. And if you look at quite a few of Rosenshines principles, they go hand in hand with teaching for mastery approaches as well, and you know, 4-part lesson designs and questioning in maths lessons and such like. But Laurie, I don't know whether I got cut off earlier. Did you mention the survey that you did on teachers as to which way they were taught trigonometry at school?
No, I didn't. You can introduce it. I can see if I can dig out the actual numbers again. It's in here somewhere.
We've done it anecdotally over the years in the problem solving work group, and when we've been attending PD sessions, we've sort of asked the group of teachers that were there, and overwhelmingly, most secondary school teachers that I've met have been taught the same way as I was taught, which was the SOHCAHTOA ratio method. So being taught the procedure and hoping that the deeper understanding comes later. So, and I think Laurie's results will show that. He's got them there now.
Yeah, so 61%. I mean, this was just, like I said, it was really anecdotal, wasn't it, Andrew? It was just, I mean, it was 560 odd votes, but it was just to gain a flavour, really. So just to interpret this, it was these are the top one are people that were taught SOHCAHTOA themselves at school and are now maths teachers and teach SOHCAHTOA, whereas this was taught SOHCAHTOA but now teaches a different method, and these are the same ideas but for the unit circle approach. I don't know, it was just something that was interesting. More detail would have been a bit better, but it was something to have a look at least.
Could run that on Twitter again, something like that.
But it takes a lot of time to undo. You know, I imagine as a child it's even harder, but as a teacher, it's taken me. I'm a bit of an older teacher, and I'm a bit slow now maybe, but it's taken me a long time to sort of move away from that procedure in trigonometric problem situations to the unit circle and the similar triangles and scaling up and down approach. So you can imagine that if children are taught the procedure first, I can imagine it being harder for them, or maybe they've got less motivation then to approach it in a different way. But what Nikki said earlier, you know, I believe it's a really rich sort of activity. There are rich activities, and the representation is rich in its use. But it brings together lots of different things and make multiplicative reasoning. It's trigonometry essentially is multiplicative reasoning, isn't it? But yeah,
I love that we can just but reference that chap, that Reggio Montanus from like centuries and centuries and centuries back. No calculator. I love that we can just reference the fact that he just scaled up that unit circle to a radius of 600 million or whatever it was, and we're just doing exactly the same idea. And it's probably, I don't know, I'm probably going to cause a riot here, but my argument, and I have bought and read far too many trigonometry based books now, and I may well be completely wrong, or it might be a chicken and egg kind of discussion, but my thinking is that this is sort of how it developed, and the trigonometric ratios, if you like, are the knock-on effect. And I feel like I'm in danger of totally upsetting people here, and I may be wrong as well, or it could, like a lot of these things, like I say, it's probably a cyclic argument. Neither's correct, but I feel like it kind of is the knock-on effect of this way of thinking, if you like, rather than the other way around. But
I think when you look at it, when you go into A level and you're looking far more deeply into it, you don't really mention the relationship between the sides of a triangle anymore. It is about the relationship in the unit circle, and that's what you develop it as. And I think I agree with you there, saying that the relationship of the sides, that's how we're used to introducing it, but actually it's a knock-on effect of the unit circle. And I also agree with what you say about the connection between direct instruction and inquiry. Like, I wouldn't, for SOHCAHTOA for me, that comes after the inquiry about, well, what's happening with the sides of these triangles when the angles change, or when the angles stay the same but the length changes. You can look at the concepts first and then say, well, this is what the relationship is, and now we can use that relationship. It doesn't have to be one or the other. It doesn't have to be discover it yourself or be told it. We can get that lovely kind of mesh between the some maths for discovery, guided discovery, because obviously it took years and years to discover trigonometry. They're not going to do it in half an hour. So a mesh between guided discovery and moving on to the understanding and the, well, how can we use it, and the teaching of it.
That's it, isn't it? It's just not getting carried away. It's like you say, it's making sure what you are doing still serves the purpose of developing them as mathematicians and keeping on top of all the different areas that they have to improve and have to study. And it's not just frills and, you know, doing it for the sake of it. And it's just nice to do it this way.
But whilst being able to give them those wow moments as you go along as well.
We did, just sort of briefly, I suppose, before we move on, we did put in a few bits about sort of where it would lead to further down the line. And you know, the model does hold strong. So again, it's probably a bit hard to see, but you've got, I mean, from the very outset, really, once the terms are defined, you've already got, because of the Pythagoras, cosine squared plus sine squared is the radius squared. So that's that, or one, sorry, I should say, because it's only cosine and sine when the radius is 1. So you've got sine squared plus cos squared is 1. Using this idea of similar triangles and multiplicative reasoning of a constant scale factor, you divide everything through by cosine, and then you get the following triangle, which would have been, these lengths, have been defined earlier on, and now you've got tan squared plus 1 is sec squared, and so on and so forth. But you've also got all those like intertriangle ratios, sine over cos must be the same as tan over 1. But you can go crazy. You can go, I don't know, 1 over cos must be sec over 1. 1 over sine must be secant over tangent. It's just so easy because it just matches up, You don't have to memorize millions of different formulas. But anyway, that's just me.
Oh, it's amazing. It really is. I've never thought about it that way.
And your passion for the work that you've been doing has really come through in your explanations as well.
Yeah, we'd love to have some references. I know you mentioned the increments and that some of the history books. You can just put them. Then we all as maths teachers, we can kind of start exploring through our own journey. So we've gone over an hour into this topic alone. I'm sure there's enough juice in it to go for like 4 hours if we had to. But is there anything you'd like to add as well, Kirsty, just before we move on, or we can move on to the next topic?
No, I think Laurie's covered everything. He is the expert on it, definitely.
It's definitely becoming more popular, isn't it? There's even a television program called Trigonometry now.
Wow.
Didn't know that. No, I did. Yeah, I did. Not that out of it. Someone else mentioned it to me. Yeah. Does beg the question, why do we not call it a trigon, doesn't it? Not rather than a triangle. We do all this work on polygons, pentagon, hexagon, octagon, but we don't call it a trigon. So, but we still call it the measure of trigons, trigonometry. But anyway, I had something that I was going to. Should we move it on before we end up? Are there any questions? I was going to talk about units a bit and see what people thought.
Yeah, sure. There's one question, but I think this Michael from Air Maths Tuition, he came in a little bit late when we kind of covered it already, but you can. He says, I like the scale factor method to measure the height. What about the width? Would Pythag have already been introduced? But,
Yeah, I mean, I suppose a quick response to that is we like the idea of the sort of, again, to sound like a broken record, but the interleaving idea or just multiple methods really. They can do the measuring for the cosine and measure the width, but if they've covered the Pythagoras, they've got another tool in their armory, so to speak. And depending on it really depends how it's panned out and how the teachers have led it and how it's played out in the class. But you could have a situation where some of them have measured it and some of them have used Pythagoras if they've already worked out the height, and you could kind of share those ideas collectively and go, oh wow, look at this, we've got the same answer but two different ways. But I think that depends where they're up to with the rest of the scheme of in their particular school and things. But
yeah, it depends on exactly. I mean, in a tutoring case, it would be on a case by case. If they have done Pythagoras, yes. If they haven't, then at some point it'll make sense.
Well, the unit circle started in year 7, and I think the common approach for Pythagoras was using the tilted squares kind of investigation. We did a lesson around that, and that was a year 8 lesson, wasn't it? I guess there'd be some you'd link up with Pythagoras and the unit circle, maybe year 8, year 9.
Shall I ask a question about units then?
Yeah, let's dive in.
It was just something I was thinking about. I was thinking about algebra really and units, and whether, not that we're missing a trick, but students come across, correct me if I'm wrong, but don't they come across things like 3 centimeters plus 5 centimeters equals 8 centimeters very early on, sort of primary school, sort of, I don't know, perimeter or wherever it happens to come up, and I feel like it almost gets banded as very, very trivial in many ways, and yet then we introduce something like 3x plus 5x, as if it's, well, often as if it's something a bit brand new. And I appreciate that we've got to be very careful with this distinction that X is representing a variable, whereas the centimetres are fixed. But I just kind of wondered whether thinking in terms of units is a way of kind of leading on to factorising in the end. But you've got 3 of something and you've got 5 of something. So be it centimetres, which all right is fixed, great, it's a fixed measure of length, or be it X, which is a variable, you've still got 3 of it and 5 of it. And as long as it's the same thing, we can collect them, because obviously they're the like terms, which kind of leads me to, I mean, that sort of, I suppose, goes into variation theory and how people might structure the questions and things. So it's always 3 and 5 of something, and then switch it to a different value. But it led me to the question: what is a term? I don't know if anyone wants to discuss what a term is, and it's certainly not a trick question, because I suddenly found myself a bit stuck on that one, and then questioned whether I actually defined it to students or whether I just got to year 10 or 11 and found that I'd been saying it on it every now and then, and that I assumed they knew what it was.
I mean, I've got a definition that I would use for a term as being, it can be a constant, a variable, or a multiplication of a variable, which is what I tend to use. But then an expression is an addition or subtraction of terms. But then you get to the ones such as maybe 4 plus x all over 5. Well, it's a division, but it's also an addition of 2 of a variable and a constant. So is that a term or is that an expression? There we go. I'll start you off with that.
I'll let someone else chip in. I've been banging on about trigonometry for too long.
Has it got 2 terms or 3 terms?
Or is it just a one term in itself?
Just one term in itself, yeah. I suppose they have to make up.
So I suppose then you get to a point is, where is it worth knowing the difference between a single term and an expression?
Yeah, exactly. It's Pandora's box, isn't it?
Yeah, it is.
Even just something like 5xy. Would you say that's one term?
One term.
Yeah.
Yeah, in my very basic, in kind of like how my brain unpicks it, 5xy is straightforward to me. It's a multiplication of a constant and 2 different variables, so it's a term. It's got no addition or subtraction in it. Whereas once you're starting collecting terms, you become to an expression, and collection to me is addition and subtraction, or addition and addition of a negative.
Yeah, I found, if I can just dig it out, from one of these really old textbooks, a Victorian one. Where's it gone? Well, this is about an expression, an algebraical. Look, yeah, they used to call it algebraical. An algebraical expression is a collection of symbols. It may consist of 1 or more terms, which are separated from each other by the signs plus and minus. Thus, yeah, then it gives an example. And then it says, for addition of like terms, when terms do not differ, or when they differ only in their numerical coefficients, they are called like. Otherwise, they are called unlike. So yeah, I think I'm kind of with you on that it's sort of separated by plus and minuses. When it gets trickier is when it's situation dependent in some ways.
Yeah.
Because we were talking about Joe Morgan put something up. What was it? Was it brackets in bundles? Something like that. If anyone just goes on to Joe Morgan's Twitter page this week, she had a screenshot from an old textbook, and it was called something like brackets make bundles or something, and that was referring to exactly what Nikki was talking about in a way, whereas if you had something like 6 lots of x plus y, the x plus y being in brackets, if you want to, you could consider the x plus y as a term.
Yeah.
Yeah.
Yeah. In computing, you call it nested. You have nested functions, and I like the word nest, like you put it in a nest. So it's a thing of its own.
That is something though, isn't it? Is that in mathematics, is that, I might have got this wrong now, is that when it's like a square root and then there's another square root within it? And it's
in computing you would a function of gx, so that gx is nested inside fx, so that's a nested function in computing, or at least from spreadsheet programming back in the days when I was doing spreadsheet programming.
Yeah, I don't know. It just got me thinking. Anyway, I just thought, would students seem to be less likely to make a mistake on, well, in my opinion, something like they wouldn't add some centimeters and some centimeters squared together because they have a bit of an understanding that one's a length and one's an area. But then we have to sometimes work a bit harder when it comes to, f and f squared. They might, sort of classic error might be to sort of try and add them as though they are like terms. But yeah, I don't know. It led me on to, when we were discussing it, Atul, it led on to me thinking about centimetre squared in general, didn't it? And my sort of dislike in a way for the notation there, because it's poor, isn't it? The centimetres, I thought this was such a great gimmick when I first sort of discovered it, and I know loads of people will be aware of this already, but centi being the Latin for literally for 100th, cent has got a lot of derivations to do with 100, and the I suffix usually means a little of something in Latin. So centi is literally the number 100th, and meter is the standard unit, so it literally is 1/100th of a meter, and so that's great. And that kind of, weirdly enough, and this is the thing that I thought was a bit gimmicky at first, I thought, oh, isn't that brilliant? It kind of follows the rules of algebra. The sort of the C and the M, the centimeters is like 100th times a meter. It kind of works. But then I came to centimeters squared and thought, well, but then the exponent, the 2, according to our usual sort of order of operations, would just act on the meters. So would it be 100th of a meter squared? Mm-hmm. Which it doesn't mean. It means centimeters times centimeters. So I'm just kind of wondering whether or not, I've only dabbled with this a little bit, so I'm really just putting it out there to hear people's thoughts, but whether we should bracket our centimeters when we're writing centimeters squared, and whether we should just put our units in an awful lot more so that students are getting practice with what is essentially going to be algebra at some stage. So when we do, I talked about 3 centimeters plus 5 centimeters, and if it's probably very easy for us to get lazy as mathematicians, as teachers really, and write 3 plus 5 equals 8, and then we shout out, don't forget your units, and we whack it on the end, and the answer magically is 8 centimeters. And I'm kind of looking at it now in an ultra sort of precise sort of mode, got my precision glasses on, and I'm thinking 3 plus 5 doesn't equal 8 centimeters. It equals 8, but not 8 centimeters. And so I don't know whether I'm being overly picky, but I wonder if for the extra effort that it takes to write it in a lot more in our sort of examples and in the way we illustrate our own work, does that then help in future? If we've got even just something like the volume of a cuboid, and they might be doing 2 centimeters times 3 centimeters times 4 centimeters, and you can really focus on the fact that the units are, well, I mean, let me see if I've got it, if I can screen share somewhere. Am I able to screen share, Atul?
Let me double check. You should be able to. Let me just change the setting. Yes, should be able to.
Should work. Okay.
Yeah.
Can I just show, this is an example with area of a circle. And again, it may be going a little bit far, perhaps. Can people see that?
Yeah.
So I couldn't quite get it to fit on. Obviously, I wouldn't try and write it sideways as well as downwards, but just let people have a look.
One of the first things that came to mind, and I couldn't remember the question that it was when I came to bits, but the misconception that because there are centimetres squared on the end, this is kind of what working backwards, is that the students had to square the value as well. So like they'd got something where it was 20, say, I'll use a different number, 10 centimetres squared, and for some reason they then put which equals 100. Because they looked at the squared going on. So I really like the idea here that you've shown that it's centimetres times centimetres, and that's why we've got centimetres squared on it.
Yeah, I'm not touting it as the answer necessarily. I'm kind of just I'm wondering whether it's what's the phrase? A stitch in time saves 9. You know, like I just wonder if going really precise and not rushing it because it's stupidly obvious to us, whether that actually is going to pay dividends later on, so that we don't have to always write it out like this. But I think there are a lot of subtle things that are really obvious for me, like this line to that line is really just making use of almost the language that 5 centimetres does mean 5 of a thing called centimetre. And one of the key words that I rushed over there was of. It's 5 of a centimetre. And if you've done all that work on of being equivalent to multiplication, then it's perfectly acceptable and to write this 4th or whatever line we're on here. And yet how often do we ever see that written anywhere? Or when do you ever walk into a maths classroom and see that? Because I'd argue it's not very often. And that actually that might, you know, if you've done work on the laws of commutativity law, I just wonder if that then makes it really clear that we can rearrange the order because it's all multiplied, and that I can see where the centimetre squared comes from now. But I think, again, I'm doing that thing where I say we when really I mean I wonder if I just made that assumption earlier in my career, that it was just obvious to go from there to the end, you know, that of course it's centimetre squared.
And I think quite a few of us will think that as well, and for a lot of students they'll accept it. They're like, we'll say, well, this is it, and they'll accept it and they won't question it. But it's only when you start questioning it that you actually realise, well, actually they're just accepting what we tell them rather than understanding where it comes from. And just the other bit I picked up in that was where you've got on the second line the 5 centimetres in brackets squared.
So put it back on. One moment. Yep.
So on the second line, you've got 5 centimetres in brackets squared. And I'm just going to ignore the pi for the moment. So if you've got 5 centimetres in brackets squared, we'd say that's 5 centimetres squared. But actually, we'll also say that it's 25 centimetres squared. But we're still saying centimetre squared for both of them, but they're different ways of writing. So point. Should we say that 25 centimetre squares rather than 25 centimetres squared? Because we've already done the squaring. Does that make sense?
Yes.
There.
And no,
and again, yeah, it's another one sort of like picking down. And somebody mentioned, and I really wish I could remember who it was, someone mentioned it on Twitter earlier, like the difference between square centimetres and centimetres squared. And then earlier this week, I was just talking to a friend who owns a carpet shop. So she deals with units all the time. And she said, oh, we got a 3 metre square of plywood. And I'm like, oh, is that a 3 metre by 3 metre? Or is that a 3 metre squares? And then suddenly it becomes very important how you're saying something.
I know people sometimes say 5, at least for the earlier bit, 5 centimetres all squared. Sometimes that all appears, doesn't it?
It's about precise use of language, isn't it? It's all about precise use of language, and we probably, I will have been guilty of this in the past, dumb it down in the classroom when really we should be really, you know, without questioning, we should be getting children to focus on that precise use of language and just stepping up a bit. And that's what, Laurie, you're talking about now. It's not just about precise use of language in the classroom, it's about representing mathematics in a precise manner. because mathematics is a precise and unambiguous language. That's what Cockcroft.
Yeah. And I'd also say, like the way you'd written this before, you wouldn't get to the point where you're saying to the students, you have to write it out like that every time, because that's not the shorthand of maths. That's not how we would write it out. But it does. But I could see that there would be a benefit with showing it to the students and introducing it and starting off like that, and then say, oh, now we understand where that's come from. We can go to the shorthand, which is the recognised way of writing it out mathematically. And this, you know what that means now.
It's an oral thing, isn't it? This is where the symbols come into their own. And reading this brilliant book on the history of symbols over time, and how it's fascinating how people, when there wasn't anything available initially, people had to come up with something and they'd use it, and then eventually someone would come along and go, that's absolutely pants, that's so misleading and so open to ambiguity, and why on earth, scrap that, let's use this. And then it was only when one of the big players like Descartes or Fibonacci or someone actually bothered to write it in a book that it'd take hold. And some of them are like amazing, the symbols, and you almost take them for granted now how good they are, but they really, really struggled, not just once upon a time, but at various points in time. And no doubt things will be improved still from this point onwards. But yeah, it's almost like if you've become a good enough mathematician to read the symbols, that's great. But you're almost referring to an oral side of things that adds its own layer of perplexity and ambiguity.
Language, CPAL isn't always what's the symbolism supposed to represent in linguistic terms, so we're actually really drilling down into the language. Just putting my physics hat on as well once again, one of the most common questions I get with my physics duties in year 10, year 11, year 9 even sometimes is, why is meters per second ms to the minus 1? And so I tell them, well, if you go back to the meaning of speed and use indices, so they're quite used to doing x to the minus 1, they use the word x, but for some reason it doesn't click that s to the minus 1 is the same as over second. So, and again, even at GCSE they need to know acceleration, so the whole ms minus 2 or meters per second gives you meters per second square, and this kind of this rigor in this dimensional analysis is just not there. And if we get it right in maths and in physics and in sciences, have this kind of consistency to get this, because often in physics and chemistry, etc., the answer of the units gives you the formula itself, like calculate the acceleration and and they give you the unit actually sometimes meters per second square, or in speed meters per second. So the formula is actually within the unit itself. I tell them, just look at the unit, the formula is there, you don't even need to remember it. So this could be done. And the other classic is I think it came up in a maths GCSE paper, with converting meters per second square into, there was a certain value, to kilometers per hour square. And to do that properly, you really need to know like your dimensional understanding, and that's a bit quite a harsh question to give that, but it just shows that you need to think about these things very carefully.
I mean, do you think that children need to have some kind of visual image of what a square centimetre and a cubic centimetre before, when you're talking about changing between, say, millimetres squared and converting to kilometres squared or something like that, or centimetres squared? Do you think that for a student to understand, they need to have a visual image of what a square centimetre or a square metre is, or a cubic metre or a cubic centimetre? Because the stuff that Laurie is talking about is very abstract, isn't it? So, going back to units, if you did volume of a prism is the area of the cross section times the length or height, then you would have, say, square centimetres or centimetres squared times centimetres. So having and within that you've got cm to the 2 times cm to the 1 equals cm to the 3, laws of indices. But it's abstract, isn't it? Do you think that they need to have this visual image of what these things are before they understand, before they get anywhere near that abstract notation.
I'd say yes. I'd say that, and hopefully I would put that in anyway, that when we come to square centimetres, we start off by looking at, they are actual squares of centimetres by a centimetre, but we count to find the area, and the same with the centimetres cubed. And then, yeah, if you're changing between centimetres squared and millimetres squared, you look at a centimetre squared and you split it up into the millimetres and millimetres. So definitely, I think the pictorial representation needs to go hand in hand with the abstract calculation, especially when introducing it.
Yeah, for those ones, it gives a feel.
Sorry. Yeah, Pete Maddox even got this net, like a flexible net with centimeter grid on it, and I think to show the surface area, you kind of overlay the net on these things, and you can see the centimeters kind of take shape. I use Cuisinaire's with the 1 cm cube, or the little cubes, to get a visualization of actually what 1 centimeter cube looks like, an actual cube, and how you can approximately fit these number of cubes into a cylinder, and then we go into the more exact formula. But I think they need to spend enough time with the real thing, like grids and actual cubes, until that abstraction is made in their head. Actually, 1 centimeter square is this little square, 1 centimeter, 1 centimeter, 1 cm cube is literally a cube, and then everything is in terms of units. So when I calculate this volume of a cylinder to be xy centimeter cube, it is actually that many cubes you could fit in, even if you kind of squish and squash them, but that's how the number of cubes you could put in.
Yeah, I have to say, I try and get a physical meter cubed. I end up using meter rules and sticking them together and stuff, and so I do that, yeah. But I think that's where the precision, doing it with pen and paper, as well as sort of the visual element of it, comes hand in hand with the science again, and those, going back to those prefixes of like centi being 100th and I don't know, kilo being 1000, and that kind of thing. Because you can have, if you had like, let's just say you had 7 centimeters squared, or should I say 7 lots of centimeters all squared. I don't know how to say it now, Nikki. Much easier written down because I know the symbols.
Yeah.
Saying it out loud is now ambiguous for me. But 7 centimeters squared, and if you know that it's the centimeters that are in brackets that are squared, and if you know that centi is 1/100th, then you could write that as 7 times, in brackets, 1/100th of a meter squared, and you could square the 1/100th times it by the 7, and your units of meter squared, they're going to pop out. It's just like, I don't know, it's a different way of looking at it.
So it's squaring the centi being 100th, and squaring the meter, so 100th times 100th, and the meter.
But something reminded me before, when we were talking about sort of poor notational convention, I suppose, over time, one of the ones that we've stuck with that kind of bugs me, maybe probably because I didn't really realize it is such a red flag for so long, is mixed fractions. And I just sort of obliviously carried on as usual with mixed fractions until I realized that the convention's dire. And I still use it, of course, because that is the way, that's the convention. But when you consider 3.5, I don't know, for anyone who's not considered it before, it's an interesting one to think about, because that one doesn't follow the usual rules, because in most circumstances in number and algebra, you write 2 things together and it means multiplication. And we have a couple of instances that are very constant where that's not the case, like place value, 2 digits written next to each other, one's in the tens, one's in the units or whatever. But by and large, two things written together often mean you multiply the 2 things, which we know causes confusion with things like sine 30 degrees. That has to come into play later about how that function works and so on. But yeah, if you consider something way earlier down the line with like 3.5, say, for a mixed fraction, it should be 3 plus a half, shouldn't it?
Yeah.
It should be. And it's sort of, it's this is concatenation, is that the right word? It was a kind of a popular trend from what I was reading a while back. They used to love to shorten things, and some of it stuck and some of it didn't. And this is one that's stuck. And I just think it explains so much as to why students get confused and find things like multiplying mixed fractions so hard, because it's not quite the same as the way other things would work. It's not, if you're doing something like 3x times 3y, and you try and compare that to 3.5 times 3 1/3, you can plumbing well understand why students get confused. It's really obvious as to why they get confused. And so again, I sort of open it to everyone else, really. I think I'm not practiced enough with this, but I'm very much trying to now make the area model fit in as many places as possible. I see that as a huge way of doing it, with something like 3 + 1/2 times another mixed fraction. I don't know if anyone...
I'm totally with you with the mixed fractions. From when I did my maths A level and then degree, and then I did other things before I became a teacher. So I was with a different career, and then I came back to teaching. When I did my maths, my calculator had the A, B, /C button. So you could put in a mixed fraction, 3 1/2, for example. And then when I came back to it, and it sounds really daft, but this is how students can get confused. With me, a maths degree could get confused when you've now got the visual button with the line box, and I wanted to put 3 1/2 into my calculator. So I used the half, and then I put a 3 in front of it, and I added to another fraction. And I'm like, no, this isn't the answer. Why isn't this working? And it's because a calculator would see that as 3 multiplied by a half, because the 3 is next to a half. Obviously, you've got the shift button to use it, but it didn't occur to me before I did that why that the 3 1/2, a mixed fraction, is a bit contentious in writing it like that, because it doesn't come up with the normal conventions of the juxtaposition being a multiplication.
It's one of my favourite little errors. That I love that.
Yeah.
I don't know if you're allowed a favourite error. I just, when because I've seen that quite a number of times where students type it into a calculator and can't for the life of them figure out why it could possibly have gone wrong, because it looks perfect. And it's only on most calculators, it's just a subtle enough difference, isn't it?
Yeah.
Like the way there's depending on the calculator, there's sometimes a subtle difference between the minus button and the negative symbol, isn't there? But
with the brackets as well.
Yeah.
But is it in Europe, in some European countries, they don't actually write mixed fractions? I believe I heard at the Maths Jam last year. So they only write in proper fractions. They don't write mixed fractions.
Yeah.
But in England we do.
I didn't know that. Yeah, I mean,
I can't say much more than that, but I'm pretty definite that was one of the things that, because we were all so surprised about it, we're like, oh no, I didn't know that one. So I don't know where it has got to the point that sort of like in England we still do write as mixed fractions, and it is perfectly normal for us, but in other countries it's not part of their notation for maths.
I mean, I'm doing fractions with someone at the moment, actually. I did yesterday, and the more I learn about this, the more I've become so careful with my language. If I say 3 1/2 really means, in the beginning, it's 3 wholes. So if you define the whole, then you've got 3 wholes and a half. So you're adding, but the whole thing is represented in numeral form, in the way we would represent it as a mixed fraction. But provided, again, it's symbolism, isn't it? And there is the ambiguity in the symbolism that two things together in digit forms mean something else, in algebra means something else, and in this kind of mixed fraction means something else. But provided they have that kind of clarity between what it's saying and what it means in symbolism in this kind of numeral form, then I think that's okay, isn't it? So I just have to it's like language as well. The English language is very irregular. 13 is not the same as 23, 33. 33 is 33, 43. All of those are very logical. 40 and 3, 20 and 3. But then you get 13, which would be 10, 3. So there are these ambiguities in mathematical language, in the English language, and for whatever reasons, and the way we use symbols as well. But provided they know these exceptions, then don't really see much of a problem with it. Yeah.
How do you tend to do it at your place, Kirsty? Would you do an area model, or would you convert it into an improper, or a different way altogether?
It depends on the teacher, really. I've seen quite a few different ways. Probably mainly convert it to an improper, just more for a subtraction, the errors with subtraction, because I've seen quite newly qualified teachers do it, in terms of the fractions and the numbers separate, or then the fractions and the numbers together. So we don't have a specific way, but I've seen majority of teachers in my department would do it where you change it to an improper fraction. So then it probably goes back to why do we have what you said about countries in Europe that don't make it, it's like an extra step for us to just make it a little bit harder for some of the kids, isn't it? I would say probably actually with me, I would probably change it to an improper.
Yeah, that's a good point, isn't it? I mean, I suppose you can see the advantage for like a subtraction. It's an advantage if you know what you're doing, isn't it? Because it's an easy.
Yeah.
and
I think I've seen people teach like adding mixed numbers where they'll talk about different options. So you can do the whole number, add the whole number, and then you can do the fraction, add the fraction, and then if that's improper, change it and stuff like that. And then as soon as you throw a subtraction at a kid that isn't where the first fraction on the mixed number is bigger than the second one, it's just completely thrown them off. So then and because they were maybe quite confident on the addition and things like that, they've then gone down a route of they just can't do subtractions, and you get quite low ability ones go, I can add mixed fractions, but I can't take them away. So I think it's just consistency as well. So that's why like changing them to improper fractions, they're then following whatever they might do, if that makes sense. So if they change it to an improper fraction and they add or they subtract, they'll do the same skills. Whereas if they're given different options for addition, they think that can be applied to subtraction because they see them as quite similar things.
Yeah. Cool. Well, I'm sure there's tons of other things as well.
Sure, yes, Andrew's got to go. Yes.
We spent so long on
for joining us. Yes, it's
nice to meet you. Okay, catch up again, Kirsty. Nice to see you again. Thank you.
Bye, Andrew.
Cheers,
Hi, Andrew. I am going to have to head off as well in a moment, but I've really enjoyed talking maths for over an hour and a half now, isn't it?
Yeah. Well, we could, I suppose we could wrap it up there, and we've still got plenty of topics that we can. I think we've got one or two more topics that we can just do another live with, and the unit circle and trigonometry one alone is invaluable. I think, in just the way the discussion is going and what will come off Twitter and the kind of sharing. Yes, it's phenomenal that you've got that manipulative. That students can experience that. Would love to hear anything more, any other references you have. Just put it out there.
Well, yeah, we'll try and ask Andrew and we'll see if we can get details sent if anyone wants to join the work groups via Zoom. But yeah, thank you for having us.
Yeah. I think we're just getting a bit of
I think that calls it to an end, doesn't it?
Yeah. No, it's pretty good going. It's nearly 2 hours. So that's great. I'll just kind of wrap it up there. And again, thanks for your time, everyone, and especially yours, Laurie, for bringing it together, thinking about it, and showing us the manipulative. It's quite tricky to do that online, but it's out there. The recording's there. So I'd love people to get involved with the recording and ask questions as well. Yeah.
Well. Thank you.
Brilliant. So I'm going to end the stream and then we can just have a